So what I wanted to do today was to carry on talking about fluid flow, pressure diffusion in these systems. And as we said last time, we're talking about transient behavior, where we have this time-dependent term, dH/dt, which exists within the relationship, which is this term here. And so what I'd like to do is talk about the other ways of doing the time integration, which relate to, we talked last time about implicit methods, where we write the particular magnitude of the equation. This equation can be written at any particular time that we choose, and we can choose that time to be time tau. And if we write time tau to be equal to t plus delta t, then we end up with a solution which we went through last time, which we call implicit. Maybe 4 difference as well, just because of where it's done in the time sequence. We can also write this equation. The equation's exact, even though it's a discrete equation, the equation is exact wherever we wish to write it. So we could also write the equation at time tau, t equals tau. And that will be explicit, just by convention. And so I'd like to explore the relationships that we get for that, and then both use EGEEfem and Comsol, if we can get to use it to be able to demonstrate that. So those are the kinds of things that I'd like to achieve today anyway. So to recap, you'll recall that when we talked about this relationship, there were 2 things that we needed to do. We needed to define this storage matrix, which in our case was given by this integral of the shape functions. So as long as we can define shape functions, which we know how to do, we know what the requirements are for those shape functions. They have to be unity at the node in question and 0 everywhere else, all other nodes in question. And so we can guess what they are, or we can use standard results to do that. So presumably we can always get these components. In the case of our one-dimensional problem, we found out that the magnitude of the stiffness of this capacitance matrix was equal to the volume of the element and divided up in some way between the individual nodal degrees of freedom. If we looked at what we referred to as lumped behavior, where we added some of the terms on the, where we added all the terms in one column and put it on the leading diagonal, then instead of this being a third, a sixth, a third, then these would add together so that they would equal a half when you take this. It would have some coefficient in front of it, which we called specific storage, which is just a parameter. It would multiply that by this volume of the element, which is just where it comes out. And if we added these terms together, then it would physically equal the volume of the element multiplied by the parameter. And so in our case, the parameter is specific storage for groundwater flow. If it's heat flow, it would be the product of density of the medium and specific heat capacity. And if it's transport, it would be typically just 1. The equation comes out that the coefficient is 1. And so we know how to for sure get this capacitance term that defines our behavior. So that's the first part of what we needed to do. The second part was then to figure out exactly how we write this time derivative. Of course, the time derivative is just shorthand for a rate of change in time of head. It can be for an individual point, or it could be for the individual nodal values. For us, it was for the nodal values. And if we wanted to write it out, we could write it out as being equal to the head at time t plus delta t minus the head at time t all divided by the time step over which is calculated, delta t. So in other words, just writing it as a finite differential, delta h over delta t. Nothing else other than that. And so since we can write this at any particular time we wish, tau, then this is also for tau and for tau. And we just had to figure out how to put it in here and then rearrange it. Those are the steps we went through. What we did last time was we wrote this particular equation, as I mentioned, at t plus delta t. And so that was how this was written. And so now all that's different is we'll write it slightly differently at a different location in time. And so if you remember, if I move this up, the idea was basically this. If you think of a graph, and if you think of this as being the behavior of the head at one of the nodes, where you look at head versus time, then all we're doing is saying that at time t, the value of head is ht. At time t plus delta t, the value is equal to a new value of head, which is this. And if we take these, I should use some nice colors because I can, then we can join these in some way. And if that's the case, then this really does equal delta t on this axis and delta h on this axis. Nothing more than that. And so since this is a constant, a straight line, and the magnitude of head varies linearly, then the derivative of head, dh dt, is constant in this. And so this actually does represent the change in head at both this point and at this point. And so no matter where we write this equation with this, we did it last time, we wrote it here, and we considered that this was true. When we write it at this point, again, we'll find out that this is still true. But what will differ, of course, is that the magnitude of the head that we write here will be at time t instead of time t plus delta t. So that's the only difference in what we'll do today. So it's not particularly involved in that regard, but that's where we're going with this. Okay, so we'll do that again. So this is the idea. And so the question is, why do we do that, I guess, in terms of the big picture? We'll find out, or we kind of found out last time, if you recall from the solutions that we had, no matter what the magnitude of the time step that we chose, we always ended up with a solution that asymptoted to the value which was correct. You'll remember that this was a geometry where it was, I can't remember if it's 1 at the base. I think it was 1 at the base, 0 at the top. This is values of head, and this was values of z. And so the steady state behavior, if I don't clutch the wrong part here, the steady state behavior was a straight line, in which case at the node where we're doing the calculations, the equilibrium value of head was equal to half, which is exactly this value here. And it always ended up at that, irrespective of how large a time step we chose. In fact, even if we chose a time step of 100, which is long after it would have reached equilibrium, we'd still end up with a stable, steady state solution out of it. And of course, we get, as we use a progressively smaller step, we asymptote to this true value for the time behavior, time discretization, which is not true. It's only true for the kind of spatial discretization that we've chosen. What we'll find out with the explicit method is that we don't always asymptote to the stable value. And you might ask then, why would we want to use something which is less stable than something we already know how to do? And the answer is that the explicit method is much more convenient because you don't have to actually form the system of equations, reform them every time and solve them. It's much more convenient in solving problems where maybe the material properties change as a function of head. And so at each iteration section, the head value would mean that you have a different permeability, and therefore you have to solve for these changing magnitudes. So for nonlinear problems, it it works out that you might want to use this. So this is always unconditionally stable, and this is only conditionally stable, meaning you have to choose the right time step to be able to get it to converge. So that's what we're attempting to do. So this is our equation. We can write it at any time tau that we choose. We're going to choose to write it at the early time step, as we said before here, at this point here. And if we do that, then we end up with equation 1. We are going to choose to write the storage matrix as a lump matrix. And if we do that, then we know that the storage matrix is, for our one-dimensional case, is going to be specific storage area length over 2 times 1, 0, 0. Please, 0, 1. Our interest in doing that is that because if we write it with only terms on the leading diagonal, then by definition, the inverse of a diagonal matrix is just the 1 over the individual terms. So in other words, it's self-inverse in this particular case. It's actually not self-inverse. So it's just 1 over these individual terms. So you'd have to invert these components on this. So I guess in this particular case, s minus 1, I think, would be equal to 2 over specific storage area times length, and 1 over the individual diagonal. So 1 over 1, which is 1, 0. I guess it's not, these would be 1 over infinity, right? Wouldn't they? But so not that, it's just the diagonal terms. And I think if you multiply those together, you should get the identity matrix if you multiply them together, by definition. So in other words, s minus 1 times s should equal the identity matrix. I won't do it, but you can check to see if that's the case. It looks like it at least could do, right? Because the product of this term and this term will be 1, because they're 1 over. So our reason for doing that is now that we can, if we know that we can invert this very easily, what we could do is we could try and rearrange this relationship in terms of this value here. So to do that, all we do is we subtract this term off to the right-hand side, and then we divide through by the inverse, and we have this term isolated, which is exactly this expression here. Number 3 is just that. And so now what we could do is this allows us to be able to, if we know what the heads were, so we know the K matrix for sure. It's just a function of the geometry. We know the storage matrix for sure. These are boundary conditions. If we know the heads at the previous time step, at time t, the early time, then what we'd like to do is be able to project to see what the heads at the new time step are. So in other words, we're sitting here. We'd like to know what this head is. So how do we get there? Well, if we know what this head is, and we know what this trajectory is, because this is dh dt, then presumably we can find out how to get from one point to the other. So it's going to be something like the head at time t plus delta t is going to be equal to the head at time t, this one here, plus delta h. And if we know that delta h could be, how could we write that? We could also write this, that delta h is equal to delta h, that's certainly true, times delta t over delta t, that's certainly true. And so that, in other words, is delta h over delta t times delta t. So this term here is just what we've referred to as h dot. And so in other words, physically, if we know what this is and we know what this gradient is, we can always get the magnitude of the new term by just writing this. So if you wrote it out in longhand, I suppose, the head at time t plus delta t is going to equal the head at time t, this point here, plus delta h, which is equal to h dot, which we can get times delta t. Nothing more. These happen to be the values of the vectors which are involved, and that's really what we're attempting to do. So the two-step process, if you like, is to be able to figure out what the gradient of head is in this time interval, which we need to know because of this and this. And if we know what the previous head is, we're able to do it. And so that's basically it. So the bottom line is that if we can take our initial heads that we have in our system to calculate what the gradient of head is in one time step, we can substitute that into here. If we substitute into here, multiply it by a time step, whatever we choose, add it to the value of this previous head, then we have an updated head. Once we have this updated head, we can go back through the cycle again and we can substitute this back in here. We can calculate what the gradient is. We can use this gradient to calculate what the update in the head is, and therefore step into time. So that's basically what's being talked about down here. We know the material properties of the system. We can calculate the gradient by using equation 3. Once we have the gradient, we can calculate an updated head from equation 4. And once we have an updated head, we can put that back. So that's really just the method. So it's somewhat. You'll notice also that we never have to invert the conductance matrix. So you know that when we solve Q equals KH, we kind of do that by doing this. It's not quite going to fit. K minus 1 and K minus 1. And so this right-hand side becomes the identity matrix times H. And so implicitly, when we manipulate this, we solve it by really inverting this matrix, finding the inverse of this matrix. We never actually do that in a formal way. We use solution of equations, but we're basically inverting the matrix. You'll notice that in this, we never have to invert the matrix. And so in terms of the heavy computational load that we have to take to do that, we never have to do that. And so because we never invert this matrix, it makes it a bit simpler to solve, even though we might have lots of time steps to do. And if we want to update, for instance, the terms of the K matrix, because it's a nonlinear problem, then we can do that easily because we never actually invert it. We don't have to re-invert it every time we go through it. So that's kind of the essence of the problem. So the obligatory 1D example is this. So go back to red. So the same geometry as before, something that's 2 meters tall. It starts off, I think, looking like with a head distributed that looks like this at a value of 1. At time t equals 0 plus, we put it to here, and ultimately over time it changes so that it goes from this to this to this. This is elevation, z, this is head, and the final value and the midpoint is a half. And so the matrix equations are the same as before. I'm just taking off, you remember that the matrix equations as we would have them before we rearranged them would look like plus 1, minus 1, minus 1, 1. The 2 comes from the other one, so these terms, I'm going to remove these in a second, but you remember that these were the terms that were there, and you'll also remember that these terms here, this is h1, which we just multiplied by this term and moved off to the right-hand side. So this first expression is with it rearranged already for the boundary conditions in the system. So we subtracted off this term, so this term here is this term multiplied by this, and likewise h3 multiplied by this. Okay, so I'm going to erase that because I don't want to make a mess of this. And so we have the conductance matrix rearranged for the boundary conditions. We have the storage matrix or capacitance matrix rearranged for those boundary conditions. We have what we've called before kind of Q star, which is the flux vectors, but also the rearranged boundary conditions in it. we've made the point that we only really have one degree of freedom that we're solving for. And so we're only solving, this is the only unknown in our system, because we prescribe this as a initial condition, and we prescribe this as an initial condition as well. So the only term we have to solve is for this central node, node number 2. This is this central equation. So in other words, when we solve this, if I can draw a straight line through here, it really is only this central equation that we're solving for. Not a very good straight line, but you get the idea. And so the individual terms would be this, and these individual vectors here. And so what do we need to do? This is what we have. This would be the equation. It's just one equation. This is the value of this term here. This would be this term here, and everything else we have. In this particular case, we want to be able to, so it's a two-step process, right? We want to know what the gradient is of head. We want to know what the head is where we're sitting. We want to know what this gradient is, and if we have that, we can project this one, and then this one becomes this one. We calculate the gradient again, and we just project ourselves forwards. So the two things we need to do is figure out what this gradient is, and then we need to update for this head. And then this one becomes, you know, the previous time step again. And so in those two steps, the first step is to rearrange this equation in terms of the gradient. So these two terms go off to the right-hand side. We divide both sides through by s. That's it. So this is this term here, which was here. And this is the dividing both sides through by this. If we put numbers in them, it's very simple that the inverse of 2 is just a half. Middle node, so it has no flux. Flux in equals flux out, and so there is no flux. This is 0. I guess this is 0. Head 1 is this top boundary condition, which is it H1? I guess I can't remember. I thought we did it going downwards, but maybe not. I guess it'd be logical if, no, I guess the top one was this one. So this is 1, this is 0, and this is 1 for these. So this is indeed 0, this is indeed 1. This value here is the same value that we have here, which is 2. And this is whatever our initial condition is. And if you think about our initial condition just from this geometry above, the initial condition when you turn it on straight away is the stuff on this line here. Starts off at unit head, and so the value here initially is this. And so, pardon me, this value here is equal to H2 equals 1 at t equals 0. We'll call it 0 plus, right? Because you turn it on. Initially it's 1, and then at time 0 plus, you turn the top node on to 0. In other words, it goes from this value here to this, but it hasn't changed any of the stuff interior to it. And so those are the magnitudes on the interior. And so we have all of those components. And so I guess the only important thing is that we can calculate what this gradient is. And it's going to be whatever this is. It's going to be 2 times, this is going to be 1, right? So 2 times 1 is 1. This is equal to 2. This is equal to 1. So it becomes minus 1. Minus 1 divided by 2 should be equal to minus a half. And so hopefully that works out to be the right thing. Is that going to be right? So this here is going to be equal to oh yeah, okay, minus a half, yes. I was thinking about what have we said about the time step? We've said nothing yet, right? So the rate of change of head at that particular location is half. So now we need to calculate what the updated head is. We know that this is also equal to 1 because this is the head at node number 2 still. It's the same as this value that we have here. This is the head at node number 2, the only node we have. This is the vector of all the individual nodes, but we only have one node degree of freedom in it. And so we have to choose a time step. If we choose a time step of 0.1, then delta t becomes 0.1. So our 10th, and so a 10th times a half is going to be a 20th. So in other words, this will equal 1 minus 1 over 20. So it would become 0.95, right? I think that's right. Maybe not. Am I doing that right? I think, right? And so that gives us a value for the first head at this revised time. So now we have a value of 0.95. So all we need to do is go back to this spot here, that the only thing that's changed in this term that gives us the gradient is that now this is equal to 0.95. That gives us another gradient of head calculation. Once we know what that is, we can resubstitute that value into here, and now we have a new value for the updated. In the second calculation, then this becomes 0.95 because that's what it was from this previous time step. This is here. This becomes the new value of this equation. So I'm not smart enough to do that calculations, but it's 2 times 0.95, which is 1.9, I guess. Well, I guess I can do it. So it's 1.9 minus 1, which is 0.9, divided by 2, which is 0.45, which is 0.45 divided by 10, which is 0.045, right? Is that right? And so you go through it and do that calculation. So it just becomes an iterative process. So we've chosen a time step of 0.1. Our first value was 0.95 that came out of it. And so let's see, this is a horrible figure, but maybe you can get the gist of it. You probably don't remember plotting graphs by hand, do you? Except for grade school when you do the number lines and this, that, and the other. You must have seen that for sure. May not remember it, of course, but I'm sure you've seen it. So this is a graph of head between 1, well, I guess it's here, between 1 and 0.5 again. So this is head versus time on the lower axis, t, 0.1, 1.0, 10.0. We did our first calculation with a time step of delta t equal 10th of a second, right? And our value was that the head was equal to 0.95, I think, right? Hopefully that was right. And so this should be this first one here. So when we did it with a time step of 0.1, our first value is here, which is 0.95. Our second value would have been at 0.2 of a seconds, and not sure I did the whole calculation, but progressively, as you march through here, these would be the points that would define this behavior. And I only know this from looking at it in the past. So in this particular case, this time step that we chose and this first value was stable. So delta t was small enough that we marched down here, and ultimately we end up with this asymptote. You can see it converts into here, and it's equal to 0.5. I guess we can go back and do it. I mean, we can do it just for kicks. What happens if we chose a time step of 1? Time step of 1 is, can I do, oh yeah, I can do it actually. We have the technology. Apparently we don't have the technology. Oh, we do. So if we use a time step of 1, so I guess we didn't have to do this. We know that this is 1. We know this is 2. We know this was 1, which you have here. And so now the only thing that changes, well, nothing changes actually, does it? Because this is still 1 and this is 2. So still the first gradient is invariant. It doesn't change. So this is still equal to minus a half. But if delta t is equal to 1, then all of a sudden this becomes minus a half times 1, which is minus a half. This value is equal to 1. It's the value at node 2, right? And so, well, it's not bad. So the 1 minus a half is equal to half. So in other words, if you do the calculation at this point, which are these ones here, and that is that the first value is equal to a half, which is curious. So now we go back into here. This value is equal to half. A half times 2 is 1. 1 minus 1 is 0. 0 divided by 2 is 0. So this becomes 0. And 0 plus the value we had before, which is a half, right? So a half minus 0 is a half. So it's actually not bad. So at time 2, which I think is this point here, it would be a half, and at time 3, it turns out, I think, to be a half, and at 4, and 5, and 6, just by fortune. So if delta t is equal to 1, it's also stable. And these would be seconds, I guess. But if delta t is equal to, I guess the next size we could do would be 2. And what do we get? So we know the gradient is going to be the same as before. So the gradient is always going to be a half when we start off from the case. So now this is going to be what? So I guess this doesn't change. This is still minus a half. But this is now 2. So minus a half times 2 is minus 1. Minus 1 plus 1 is equal to 0. And so the first time step we end up being for 2, which I guess would be this point here, right? So, or is it here? I think it's here. So 2, 3, 4, 5, 6, 7, 8, 9, 10. I think it is this point. So this one would be minus 1. Sorry, this would all be all the way down to 0. If we calculate it at the next time step, then what do we have? Well, I won't bore you with the calculations. What you'll find is that it'll jump up to here. So it jumps up to plus 1. The next one, it goes down to 0. It jumps up to plus 1, goes down to 0, and it oscillates. And so if you choose a solution which is a time step which is too large, it is unstable. And so we cross that threshold as we go to this. And it changes from being a nice match of the real behavior to being the stable long-term solution, but wrong at earlier times, to being rather wrong. And I think if we used a successfully larger time step, you could follow exactly where that goes. And so the point is that the explicit method is only conditionally stable. You have to choose a time step which is small enough to be able to do it. And once you get beyond that time step, then you're in a bit of trouble. Okay? The other way to look at this, so those points, if you can read that, those are basically the points that are being made here. So it's steady at 1, but at 2 it's unstable. So the other way to think about this is if we come back to this point here. Oh, not there. Is that this is kind of getting a bit messed up. I found this new toy to play with. Does a decent job. So if we look at this figure, then what we can see is that we could do a couple of things with this figure. So far what we've done is that we've chosen, apparently we can't change colors anymore. Oh, that's because of that. You can't get a colored eraser? Okay, let's choose something. So what we've done is we've chosen, first of all, we did this for the implicit one. And we did this for the explicit one. And as you recall, all we did was we actually wrote this equation at that particular location. So we could write it either at this point, t plus delta t, or we could write it at t, and we ended up getting these two very different solutions. Implicit, unconditionally stable, explicit, conditionally stable. But what we could also do is there's no reason really why we couldn't write tau is equal to some other location. And so what we could do is we could use this separation between these two locations, which we know is delta t. And we could define a value of time, if you like, as part of that distance. And we could write another variable which we'll call lambda, which is equal to the time where we write our solution step divided by delta t. And so in other words, you could think of this as a graph between these two places where we plot this value lambda, and at this point lambda equals 1, and at this point lambda equals 0. That's just by definition. So if t is 0 at this point, divided by whatever this separation is, it's still 0. If t is equal to delta t at this point, then by definition lambda is equal to 1. So you could think of lambda as kind of a scaling function between the two. And if you do that, then we could think of trying to write an expression that allows us to choose a position between these 2 points. And that expression is what's going to come up on this final little page here. And that's this top expression. I'm going to try and make it smaller so I can do this. So in other words, just to reiterate, I think I can draw across 2 pages. This is our graph. This is head. This is time. This is time t. This is time head at time t. Different color to represent this. Getting very fancy with this all of a sudden. This is time t plus delta t. And this is the head at time t plus delta t. And all this is where this is going is that we might like to write a head at some intermediate time. And this intermediate time would be the head at time lambda, for want of a better term. And this is where, this is t lambda, if you like. And so by choosing a value of this lambda, as you scale across from here, where it's equal to 1 at this point and 0 at this point, this is just our scaling for lambda, right? Remember from this? It's just this idea here that it scales from one to the other. Then we're really kind of writing a shape function. Actually, it's actually the term that we used for to get the head at any particular location. So in other words, we can get the head at any particular location. Maybe I should call it h tau, because tau is the location we're choosing. And it's equal to head at the initial location, the difference between the heads, which is this amount here, this is delta H here, and this is delta H here, and all it is the multiplier. So in other words, if it's 0, you're getting the value exactly at this position here. If it's equal to, lambda is equal to 1, then you're getting the value, the delta H, equivalent to this value, just by similar triangles, essentially, right? And so the idea is that instead of writing our equation at either t or t plus delta t, we can write it at any intermediate point here, which is what we're going to do. The gradient of head dh dt doesn't change, right? Because it's a linear value. It varies linearly between here, so the values are constant for the gradient. And so this equation 2 is always going to be set. It's not influenced by lambda at all. But if we substitute this value into here, then it certainly will change. And then we get a slightly more complicated equation. And I'm not going to go into the equation, but other than mention what the outcomes are. And the outcomes are kind of important because if we write it at the end of this range, at this point here, then by definition, lambda is equal to 1. If lambda is equal to 1, this is our implicit. I think also referred to as backward difference, I guess, because you're casting back to figure out what the head is, I suppose. It seems to me that it should be forward, but I'll take it on trust that these notes that I made many years ago are right. And so this is the value that we did for the implicit method. If you write it at this point here, then lambda is equal to 0, and you end up with this forward difference. And you can write it anywhere in between, but the most famous of the locations at which to write it is halfway in between, so where lambda is equal to 0.5. And if you do that, you end up with this value here, which hopefully you can see at the bottom. And that is named for its originators, Crank and Nicholson. Crank must have been a professor at Oxford. Some of you, if you look at the classic book on diffusion by Crank. And so the important thing about this is that this boundary of lambda equals to a half, and there's no reason why you can't use any location between 0 and 1, but lambda equals to a half is this boundary between unconditional stability and conditional stability. .5. Stability, which is written at the bottom of the page. So 0.5 is good. It's unconditionally stable, and anything less than that, 0.4999999, is only conditionally stable. Which means delta t has to be small enough to be able to give you a stable solution. That's it. And so again, it comes to the point, well, if it works just fine for being unconditionally stable, and it's relatively straightforward to use these, why would we ever want to do this? And it's because it's the way that we deal with it. When we solve the system of equations explicitly, we never formally invert the conductance matrix. And so it's relatively efficient for nonlinear problems where something is changing as a function of the head, for instance, in our case, and therefore changes with time. All right? Okay. Yeah.
Why would we want to use half?
Because the errors in the approximation are less than for 1. So the finite difference approximation, when you do that in time, is less. That's why. Yeah, good question. That's why. I can't prove that, but that's the reason. So using a half is because the finite difference dh dt that we've used is actually, I think, because it's calculated both. So you sit in the middle of the time step and you look ahead and behind, and you get a better approximation for that. All right. All right. So let's mess around with. So I want to do two things. I wanted to come back to use Comsol again today, but I wanted to use EGEEfem today as well. So this maybe. Oh, look how big this stuff is. You can see that, right? Now, finally. Even though can you hear me? Can you hear me, Ben?
Oh, sorry, I turned the hearing.
Oh, you turned the hearing now. I wasn't sure why you're sitting so far back. All right. Anyway, so let's mess around with this. So what did we do? Yeah. Fine. So let's look at EGEEfem again. So you remember our geometry that we're dealing with. Maybe I'll pull up. Don't need to pull up a blank screen because we have these figures. This is the geometry that we're dealing with. You'll remember that. Maybe you remember that when we dealt with it in this particular problem, what we did is that instead of working with this particular geometry, what we did was we started off with the heads everywhere being zeros. Just because of the way the code works, and then all of a sudden switching it to be 1 at the top, in which case the solution in time goes out to look like this, then this, then this, right? We have two elements. They're each of length 1. They have a conductivity value of 1 and a storage value, specific storage of 2. Everything is localized in terms of the conductance matrix and the storage matrix for these particular cases. And so if we look at what that looks like here, you'll remember this is element number 1. It has material type 1 and nodes 1 and 2 going down from the top second. Element number 2 has material number 2 and has nodes number 2 and 3 as it goes down to the base. These are the coordinates of those nodes. 1 is at the top, 2 is below it. Node number 1 is at the top, node number 2 is below it, and node number 3 is below that in terms of z going downwards. And we define the boundary conditions. So the boundary conditions that we have, if we have a defined head condition, which we have here, then the code for that is equal to 1, meaning that h equals prescribed. And if it was a flux boundary condition, which it is for this intermediate point where no head is prescribed, or you can think of it where head is not prescribed, then the code is the opposite. And we use that code to multiply by the magnitude of the boundary condition. So the magnitude of this boundary condition is a head of 1. The magnitude of this boundary condition is a head of 0. And so it's just a convenient way of doing the multiplications, so that if you remember when you do this, it's exactly this, right? When you multiply the value of the head by the boundary condition, so in other words, the head here is the value of head h1, and you multiply it by this code, if you like, which is 1 if the boundary condition is a head and 0 otherwise, then 1 times the head gives you this value here, times this term here. You can use the same algorithm here in that the head of this point here, the initial value would be head 2, but the code for this, because the head is not prescribed, this code is 0. So when you multiply this by 0 and subtract it off to the right-hand side, you don't end up with a term in this particular location. You end up with minus 0 times h2, which is 0. And so that's, in case you wonder why that coding is there, it's just the coding that's grown up with FEM because that's the way that it's easy to deal with the boundary conditions. So in other words, you can multiply this whole equation through by the whole load vector with these codes attached to it, and take everything, subtract everything from the right-hand side, and that's it. And so that's the rationale for it. Maybe more than you need to know right now, but or may ever need to know, but that's the reason for it. So this is the code, and this is the value of the boundary condition. 1 at the top, 0 at the bottom, and undefined. You could call the middle one anything you like, because it wouldn't care, because it multiplies it by 0. All right? Everything's localized. So when you go into the element, you come into the element with no conductance matrix, nor any capacitance matrix, the S matrix, nor any mass matrix. We won't use that in the stuff we're doing. It's for dynamics, but those would be the 3 things. Just because, well, actually it might be worthwhile writing out. If you solve a structural dynamics problem, you end up solving a system of equations that looks like this. That force is equal to mass times acceleration plus damping times velocity plus stiffness times displacement. So we've kind of seen a bit of, in our particular system, we're solving something that looks like flux is equal to storage times pressure gradient, head gradient, plus conductance times head. These are our dependent variable matrices. So this is the problem we're looking at now. We operate on the nodal values of heads, displacements. We operate on the nodal values of rates of changes of those parameters. This is called damping rather than capacitance. And in structural mechanics, we have a mass matrix and an acceleration term, rate of change of velocity. So this is dv dt. And of course this, this is Newton's second law, right? F equals ma. And so that's where that comes from. And so when you look at the rationale of doing these matrices, all of these individual terms, the conductance, the storage, and there is no equivalent term for flow problems, but this is an inertial matrix. All of those are localized into the finite element matrix. Stiffness, capacitance, mass. And so in other words, if we wanted to, what we do, I guess we just add this here. I don't want to completely screw this up. I probably will, of course. We could do this dot, dot, dot. And this would be ML equals, it would be area times length times density as a masses multiplied by this matrix here. And divided by 2, yes. And so in the same way that our capacitance matrix is the volume times the parameter storage defined for that element, this is the appropriate term for this, which is the area times length. If I could spell properly, it's not going to like this, is it? Area times length is volume times its density divided by 2. Add these 2 terms together, it's 2. So the term that populates that is just the mass of that particular element. And what it would be is if you imagine a framed structure, and a framed structure would be, like the ground with a high rise, quite topical with the tragedy in Taiwan, of course. So this would be what a finite element model of a building would look like. Is for this particular element here, it would look like this. And all that you do is that you'd be putting a mass on each of these beams for this element here, that there'd be a mass here, which would be lumped at that particular location, and a mass here, and it would just be equal to half of this mass applied on each. So that's where the word lumped comes from that's used here. You lump the mass at one location. So now when you shake the bottom of this by moving it backwards and forwards very quickly by the ground acceleration, it will respond in some way to be able to behave. And you could calculate what the vibration of that particular system would be. All right, so this gets returned back here. So those are the changes. So how does that get used in this relationship? Everything, all the activity is shown here. And that is that you can imagine we start off at some initial time, we choose a time step, and we choose a way to solve it. If we're just solving f equals kh, the static case, then we make this number 1 here. And that's the cases that we've been solving before. So I guess if we did that and ran it, we might get a solution somewhere. The solution would be that the head at the upper node is 1, the head at the middle node is a half, the head at the bottom node is 0, and we did the calculation last time to look at Darcy's law. You should never, ever, if you learn anything from this course, you should ever run any program or trust any program without checking it against some really very simple solutions. Last time we calculated from Darcy's law what the flow rate should be. It should be 0.5 out and 0.5 in. You can't quite see the negative here. Now you can. And this is the value here. Okay. If we make the time step equal to something else, then this is the one we looked at last time. We did 30 steps. We increment each time the time step by delta t, whatever we choose. We calculate a value of the conductance matrix, and we divide it by the load vector. That's basically what we do, right? F equals KU. I know this won't be recorded for posterity, but we have Q equals KH. You could think about multiplying this by 1 over K, which we write as K minus 1 in vector language. And therefore, in other words, taking the load vector and multiplying it by the inverse of the matrix, which is what we're doing, gives us basically this term here. And so when we look at exactly what this is doing here, this is the load vector here, included in this part, divided by k. Yeah, I guess this is the division, right? This is the divided part. This is 1 over k, this first term, and this is the q term of these two parts. And we went through that last time. So the third one is what we've just talked about, explicit method. And that is that we do the same thing. But now what do? We calculate a value for the head at time t. We add to this the value of the gradient of head, dh dt, which is this term here. And so in other words, dh dt is the value, I'm trying to think, it's the value of this expression. Not this, right? On the page. It's this term here. I guess we can look at it here. In other words, it's this expression here. Whoops. Who knows what's going on? Should try and use the pen that's in my left hand. Oh, that's not good. Oh, that is good. So in other words, it's this term here multiplied by the load vector to give us the gradient. And then we take the previous head and we multiply the gradient times the time step to get the next head. And that's physically what's being done here. So this is the previous head. This would be the gradient of head calculated in these two parts and the time step. And the gradient of head would be 1 over the capacitance matrix. So this is 1 over the capacitance matrix and the load vector manipulated. And this is the load vector manipulated. Right, so that's all this. So let's see how it runs. This I haven't done that. Let's see. So we know that if we make it run the way we hope it can, so this is this. We know that if the time step is equal to 0.1, then it works. I don't want to do 30 time steps. Maybe I want to do 3. Yeah, let's try 3. And so if I run it, let me clear it first and then run it. Just makes it a bit simpler. If I run it, it comes to the end. So remember that we're starting off from 0 all the way down, and we're changing the top one to 1, and so the half point will go to 0.5. So it'll start off at a small number and go up. So at time step 1, it will equal 0.05. That was the change we had before, right? The first time step went down to 0.95. So it changed by 0.05. It changed the next time by 0.045. So I think that's what this is here. And yeah, so it goes up. So these are the same results that we had before. If we change it so that we actually do 30 time steps, and I zero it, or clear it, then hopefully it should run to the case where, well, not far off. It's 0.4788, and I guess it was 30 time steps, each at 0.1 of a second, so that's 3 seconds. And so if we were to compare it with this value we have here, then on this figure, I think this is 2, and I think this is 3, so we're at this point here. And if I look at this, then this point here is about 0.5 and 0.525, which would actually be less than 0.4, so it would be 0.475. Is that what we got? I think it was actually, wasn't it? I astound myself. Amazing. And it's all unrehearsed. And I'm sure you can believe that if we made it 50 time steps, then apart from having to look a bit further, then it should asymptote, I think, to basically 4974. And so we can go on. If we choose the time step, if we change the time step, and if we do it back for just one value for 5 time steps, if we choose, what was it that worked halfway as well for us? 0.5 worked part ways well, right? Do you remember what we got when we used half? 1. It's the same value. I think it went to 0.5 and stayed there. 0.6. Oh, that's kind of curious. Why is it doing that? That's interesting. It's not doing that. Has it actually taken? So it goes to a quarter. Goes to. Actually, it asymptotes to 0.5. So. Which one was it that didn't work? 0.5 worked just fine. 1 ended up being unity. Again, blank it out, run it, and for all times it goes to 0.5, 0.5, 0.5, 0.5, 0.5. It flatlines. And let's use 10. Let's zero it out because we're going to run it again. What will happen when we use 10, you think? What's your informed opinion? Yeah, we go crazy. So yeah, there you go. See. So first time step, it goes to 5. This is just the middle, only the nodes that are changing. So it goes from 5 to minus 40 to plus 365 days a year for some reason, minus 3280 plus 29. So it's oscillating and it's growing progressively larger. So let's see. We got a little bit of time, so why not? Let's see if we can pull up Comsol, just because we can. I'm curious to see if it runs in this Xseed. It's very big on the screen, isn't it? I'm curious to see how it works out. Any questions while we're queuing this up? It's pretty exciting stuff, isn't it? Was that a forced agreement? You didn't. I think it's good. I think this stuff is great. All very logical. That's what I think is cool about this. Well, let's see how it works. See what it's going to tell us. It seems to be taking its own sweet time. Oh, that's not good. Login. That's not doing anything.
I'm getting the same error.
You are? Oh, fine. Probably you're blocking my signal. You're destroying the bandwidth. In fact, I hope you're not reading the news and destroying the bandwidth otherwise. Yeah, it's kind of a pain, isn't it? Well, no great matter. We can do that some other time. So, it's not working. So we can't do that. So should we go back to EGEEfem? I don't think we need to, but anyway, I think you get the point. So that's where we are. I think that's really... So if you look at kind of the trek that we've taken so far, we want to be able to look at all of these different behaviors. Solid mechanics, the 3 flow behaviors: fluid flow, mass transport of dissolved species, and transport of energy. We recognize that the 3 transport ones are all scalar variables of either pressure, concentration, or temperature, so they're easier to start with in terms of the finite element equations that describe those behaviors. We've talked about pressure diffusion, which is the fluid flow equation, Darcy's law. We've looked at it in terms of defining how it gets localized into Q equals KH, the finite element equations for steady state. And we've taken the next step to see how we do it for transient behavior. So now we've got that taken care of. And so now, as we forge ahead, the next task that we have in the logical progression of what we'll deal with is that now we're interested in the next iteration. And the next iteration will be where we still haven't solved all the transport problems because we haven't solved for heat flow and mass transport. And both of those expressions differ from the fluid flow equations in that they have one extra term. And if we look at just strictly the flow equation that we've dealt with so far, it's always looked like something like specific storage times a change in head with time, the capacitance term, is equal to hydraulic conductivity times the rate of change of head in space, the second order of that. If we look at transport of mass species, for instance, what we'll find out is that the expressions look like a rate of change of concentration with time, which is equal to a term that includes diffusion according to Fick's law. So this was Darcy's law. This now includes Fick's law, but with an extra term, an advective velocity and a concentration gradient in space. And so clearly, when you compare these two equations, which I've written above each other on purpose, is that now we have a new term to deal with. and this is advection. So this is, in other words, is how material gets advected through the system by being carried through by the velocity of the flowing water. It's not any different. The analog I always use is if I have a beaker of water and put an ink drop in it, then it can diffuse in that beaker of water. If I carry the beaker of water to the other side of the classroom, then it's being advected across by me physically moving it across. And this behavior isn't really very much different from that. What you'll note with this is that when we talked about the behaviors, we said that anytime we have a term that looks like d2h dx squared, this always looks like this. Right? Anytime we had a term that looked like 0th order, so this is 2nd order, 0th order, which was d dt, so no spatial dimension, times h. Then we had something that looked like what we just finished dealing with now. Just the shape functions, dv. And what we haven't dealt with is what the term looks like if we have a single order partial differential in space. 2nd order in space, 1st order in space, 0th order in space. And it looks something like B transposed A times V. Something like that. Can't remember exactly. So shape functions, derivatives of shape functions, and velocity. Velocity is the multiplier on here. And so that's kind of the punchline. And so the other punchline, I think, is that once we have these relationships for 2nd order, 1st order, and 0th order, actually we've pretty much got all of the ranges of partial differential equations that you could imagine in large part. And so we're kind of at the end of what we need to talk about in terms of dealing with that. And the only thing is, what we now have to deal with is how do we calculate them when this is no longer scalar, but when this is a vector, such as in mechanical behavior. So that's kind of where we're going. That's the big picture.